Okay, ladies and gentlemen, thank you for coming back so promptly. Bob said he didn't want a big flowery introduction, so I guess most of you probably know him anyway. We call him the man, the living legend of electronics. He's not with us today, but he's here at least in spirit, and he wanted to do this presentation. How long have you been doing it, Bob? Since pretty much the beginning of the Smart Group, I guess.
A little bit before then.
Yeah, even before then. So, yeah, we won't say how many years because I don't want to embarrass him. But I will just let you have the room, Bob, and I'll pick everything up if we do questions at the end, and you ask me the question, I'll relay it to Bob. Bob will give you the answer to the whole room. So we have everything set up and running. So I cross my fingers that it's all going to go well, Bob. Over to you.
Thank you very much, Keith, and welcome to everybody in the room. I'm really the warm-up act for Martin Wickham and Dr. Chris Hunt. And of course, Keith is just holding everything together as he does so well. As I get older, more bits don't work, so unfortunately I've had to have a couple of operations and things, and that's just one of the reasons why I'm not with you. Actually in the Plaza Suite Ballroom, according to the running order. Anyway, moving on. I just want to talk practically about my experience with QFN LGA packages and some of the issues that I've seen over the last few years and some of the failure modes. A number of the technical committee suggested that they wanted to hear this particular presentation, so hence I'm doing it. So just as a little bit of background, in 2021 I did a survey, and one of the questions was looking obviously at components that gave people problems in manufacture, and the LGA QFN really was sort of number 3 in the pecking order. If you look at the return, there was about 100 people contributed to this particular survey. So QFN has given us problems over the years, and I'll address and talk about a couple of those particular issues. For those of you who are not aware, internally the packages generally take on these forms. It's a plastic package. It's really designed for consumer and mid-level reliability products, but is used extensively on lots of products today. You can see the type of build you might have with one of these packages, with a single peripheral terminations around the edge of the plastic. And these packages are made basically like a chocolate bar. So if you have a Cadbury's chocolate bar or any chocolate bar, that's how they're formed. And then they're broken out and singulated to form the components that we know and love today. You can get 2 rows, you can get multiple rows of terminations, as I indicate here, on some of the more advanced packages. These are less common over the last few years, but they are still being used. And if you look at the bottom of some of these packages, you can see some are there for functionality, some are there for power, some are there for shielding. So not every one is a critical interconnection. Again, that's down to the actual design and functionality of the package. I started off doing QFN processing and trials and tests quite a few years ago when I couldn't afford components, so I made my own. And this is just a simple example of a configuration, a daisy chain configuration I used at that time, where you see the center pad that you're familiar with on most of these designs, with and without via holes. So just an example. The packages I actually made were on a multi-sheet, as you see here. They were V-scored. They were slightly larger than the packages you typically see on a printed circuit board, but they were very cost effective to produce. And I used these in a lot of the standard trials that I conducted over the years. Now, one of the things I always look out for when I'm sort of doing processing of these parts is some of the things that quite often go wrong. And I love to talk about things that go wrong, because if you find the root cause of something that's gone wrong, generally speaking, you can eliminate it happening in the future, which is kind of nice. And one of the common things that people perhaps don't pay attention to is displacement of paste. And with the use of X-rays, you see in this example, you can print a package with your design rules, whatever you care to use,
and then you can look at the degree of displacement, which then can lead to other processing issues. So if you have X-ray available, then it's a useful tool to use during your NPI builds on products, just to get a feel for it. Most people are aware how soldering works, but these two video clips, which were made on a video simulator system a few years back, and this was me trying to understand exactly what happens during the reflow cycle, what happens to the flux, what happens during reflow, is there any movement taking place, is there any floating, which you can see on the right-hand side, where you've got literally the outgassing of the flux taking place during reflow. So understanding and seeing what's going on in any process, I personally think, is a very, very valuable tool. It allows you to understand process issues and hopefully to solve them. So in terms of design rules for QFNs, these are just standard ones. You can see here a standard configuration of outer terminations, the center, large area, and vias. Now, one of the most common problems I come up against is people putting too many via holes in the center when they don't need to. I've been in situations where people have followed the design rules from the supplier when they didn't need that functionality. And that's one of the root causes which can give us problems with voiding and lifting and floating of parts. So understand what you actually require of your design and don't try and maximize the number of vias when it's perhaps not necessary. In terms of yield and improvements, trying to eliminate solder mask around the functional pads on the outer periphery has a number of benefits. One of them certainly is cleaning and cleanability, because it removes material between those terminations which would prevent you or reduce the effectiveness of the cleaning operation. And I know a couple of people in the audience would echo those views. If you are going to use vias, and that's fine, because we need them for some functionality, then consider using resist donuts. And I've used this technique many times. This reduces the loss of any material into the via, and the via still remains open, but the via still provides an avenue for volatile material to escape during the reflow soldering operation. And it reduces the possibility of the components floating during reflow. So it's one of the things that I strongly always recommend to do this, because it does improve performance. If you can reduce the number of vias, then that also has an impact on our performance. Another thing that I have tried with one particular company is improving thermal performance of a package where temperature cycling was a concern, and actually generating standoff. And in this particular case, we put resist around the corners of the center pad. What effectively this is doing is increasing the standoff of the package, increasing the standoff of the solder joints, and then theoretically improving the joint reliability during temperature cycling. It's not something that's common, but certainly I've done it with one particular customer. Back to the vias for a second. Again, an old photograph of mine, and what you can see here is the loss of solder volume to the vias. Now, if solder wets beautifully, wonderfully, it actually pulls the package down to the surface of the board. So consequently, that displaces solder even more, and possibly could in fact cause solder shorts around the outside termination of the part. So anything that stops you changing your process, i.e. losing volume of material you've actually put there for a purpose, has got to be an advantage. Now, actually seeing what's going on, and this has been a development that's been going on for a few years now, the ability of a couple of different X-ray suppliers to show you what's happening during the reflow cycle. So on the top left-hand view, you see a video, and you've seen the solder reflow underneath the package, but you can also see the solder going to the vias, which is the point I'm making. And on the right-hand side, again, you've got an example of resist donuts, which are preventing the solder going into the vias. So, and in this particular case, we've got very little evidence of voiding as well in this particular example. Not everybody has these capabilities, but knowing they're available as an evaluation tool is very, very beneficial. Here's a simple little problem as well. Again, we've got a standard pattern. You can see multiple deposits of solder paste on the center pad. These vias are actually filled with solder mask. But unfortunately, when you actually place and then reflow, what you're actually getting is blowback. So the volatile material can't escape at all. And on this particular product that was being built, you can see solder shorts to the side. Now, you wouldn't generally expect to see solder shorts on pitches of this type. So there had to be something different other than poor placement, poor printing, etc. So doing some trials, we were able to establish what the root cause was. So try and look, not the obvious, sometimes it's the less obvious that causes some of the problems in manufacture. And just to back up, this is going back to 2009, a paper that I did. Well, David Bernard did the paper. I just sort of was there, where we looked at the performance difference between using solder mask around vias and not around vias. And the green line right at the bottom is the lowest percentage of voids in the solder joint, which sort of backed up what I believed and I've demonstrated in the past. So there is a value in that particular area. Now, voids, there's obviously lots and lots of discussion, just like with via holes in QFN LGA packages. And if voids are not an issue to you, then why work to a tighter specification? If perhaps a product can operate and not have any impact with 30% or 40% voiding, then why are we worried about it? But if you do need it, what is the way of reducing it? Well, another one of the ways is using vacuum. And this is just an example of me running on a production line, same pace, same print, same package, but all we did was turn the vacuum on in this particular example. And you can achieve this with convection and vapor phase, but this example was with vapor phase. Now back to what causes voids. You've all know all the long list of things that we evaluate, but here's a classic example of a board outgassing. And this is a board from that center pad outgassing, and these have been actually filled with an epoxy. So the vias have been filled with epoxy to enhance the reliability and improve the performance of this particular package. But what it did was actually create even more voids. And this is something that I demonstrated just with my simple oil test. Some of you will be familiar with the oil test for outgassing from PCBs. This is just on the surface of the board where we've got a flat surface and we're looking for volatile material coming out of the plating or out of, in this particular case, between the plating and the vias. And this would certainly, as it did, create voids within the solder joints. Now, most people don't clean QFN LGA packages, but they can be cleaned. Here's an example of inability to clean, but understanding the cleaning chemistry and its compatibility with whatever flux material you're using is key to effective cleaning. Those two things. It's not the power of the machine. It's not the solubility of the material. It's not the cleaning performance of the raw cleaning material. It's that combination and getting that right. So in this particular example, as you can see, poor performance. And in this example, again, poor performance. But on the right-hand side, you can see that the material is starting to perform better, but certainly material left behind. And before you ever consider spending all the money you will have to pay for SIR and ion chromatography, do the simple things first. Do the simple glass slide tests, etc., to look at solubility of materials to make sure the performance is and can be as good as these examples. And these were just done in a batch system. Each of the processes was optimized. And again, we've got good performance and total solubility of the flux residues. Now, when we talk about the next more advanced testing that NPL has done for many, many years supporting customers. This is an SIR test board that I used on a production line when I was working with Chris Hunt on a Sweden production line project. We modified the test board to include QFN LGA packages, as you can see here, again in 2 loops to allow us to do measurement. And you can see the packages. So we printed and dispensed, placed in the normal way, placed, reflowed, vapor phased, convection reflow, all those sort of nice things. And there's a lot more information I can give you on this, but this is just simply giving you a view. And we put this through the process of SIR testing that most of you will be familiar with. And this is just a reference sample board, which is part of the testing that Ling Zhu does for many customers at MPL. And you can see what I refer to as the squiggly lines or the resistance values. And here's an example of a failed sample. And you can see 3 or 4 points of interest well below the level that would be considered unacceptable for SIR. So that's standard SIR testing. But during my time working with Chris and also Martin, these guys have worked and introduced condensation testing, which I think is a real benefit. And of course, Martin will be talking about it a little bit later on. This is my thumb, and my wife always complains that I should do manicure on my nails before I use videos like this. But anyway, the whole point is condensation. You actually want condensation, but in a controlled way to test the viability of materials, fluxes, conformal coating, etc. Traditional SIR, you don't want condensation. You want a humid environment to show up variations in the process. With condensation, it's a faster test, but I'll leave that all to Martin to discuss. But here's just some examples from the Swedish project that we ran doing traditional SIR and condensation testing. You can see the dendrites that some of us unfortunately are familiar with, hopefully on not too many products, only on test boards, but this is the type of failure mode that you might see. So cleanliness assessment can be done in a number of different ways, but I like to do different things because sometimes assessment can be very expensive. So how can you look at something and do initial failure analysis cost effectively? Well, this is an example where I take a test board that I know has failed or showed some evidence of failure, and I microsection it, but I microsection it through the board. So what you're looking at is the back side of the QFN in this particular case. And as we get slowly closer and closer and closer, we can actually see potentially the failure point, the point of failure, but without destroying the information. Because if you're doing evaluations and you take the QFN, you've destroyed the information. You haven't got the failure analysis data anymore visually. But using this technique, it's simple, cheap, quick, and it's a useful tool. However, there are obviously some other better tools as well, which we'll mention in a moment. Also, when you're looking at QFN, some of the more exotic QFN LGA type packages, this is an example of a very large package, but where the solder mask the pad is recessed below the level of the solder mask. And this, when you go into placement and then go through reflow, can actually give you non-wets. So if you look at this here, a close-up just shows a simulation of a non-wetted pad. So the actual design of the component can give us a few issues. You don't tend to see this type of issue with traditional QFN packages because they don't have solder mask there. And this is just some examples of what some people refer to as dog bones and sausages underneath this style of component. And part of the reason is the volatile material can't escape from that cavity that I showed you earlier. And that is a contributor, or quite a large contributor, to the voids that we actually see. And also the push out of solder in a liquid state away from the pads during the soldering operation. Now, we all want to produce, test, and get a reliable product. And more recently, there's been interest in immersion testing. And it's something that amused me and I thought was quite a useful tool. And if you refer to conformal coating in electronic applications, it's a textbook that I would suggest you read. It gives us an indication of a German test for immersion, which has been around in the industry for conformal coating for quite a few years. And in simple terms, we take a product that you've produced and you put it into a bucket full of water. It can be pure water, it can be a salt solution, a saline solution, or it can be some other chemical that you want to assess the performance of the coating or protection against, and then we watch what happens. And in this particular example, I'm just showing the interaction under power of this particular sample that we've immersed. And again, if you go into close up here, you'll be able to see we're getting a reaction taking place, although fairly small reaction from some of the other small parts on the board. Again, I started doing this just with the QFNs after the Swedish project a few years back. And you can see I'm switching the power on and switching the power off. And you can see the reaction. But this particular board has in fact been conformally coated. So clearly, perhaps the conformal coating wasn't done as well as I could have done, or it's the specification, configuration. There's lots of variables there. Two of the well-known conformal coating companies have done similar tests to this. And if you speak to those that are exhibiting at the conference, they may be able to give you more data on their test results. And I know Martin is going to be doing some work in this area in the future. If we talk about conformal coating, one of the other things which is not talked about a lot, but is and has been seen on a couple of technical papers, is making sure you match the thermal performance of the materials and when you're doing temperature cycling. We know that with BGA, if you get a lot of conformal coating, particularly an epoxy resin, underneath the BGA and temperature cycle it, you will stretch joints, you will deform joints and possibly break them. But the same can be true of QFN packages. If you have conformal coating, which is penetrating underneath the packages, you've got to think about that as another potential failure mode that you might see within the industry. I personally haven't seen it myself, but I have read 2 technical papers on this particular subject. Now, in terms of failures in the field, most of the failures that I've seen have been cleaning and contamination relating. This is the first one. And again, I'm trying to show the dendrites so you can see them without destroying the information, which is what failure analysis is all about. And what you can see here is some dendrites formed. They're underneath the package. They're sort of below the package.
Hi, Bob. Can you still hear us?
How's that, Keith?
That's better.
Okay. So I'll just step back to the one slide before. So on this particular one, where you've got an example of dendrites, you can see under X-ray, and you can see the dendrites forming between pads underneath the package. The story behind this particular device is it's reflow soldered using a no-clean technology, and I'm working for the people who have got the problem. And what I wanted to try and prove is that, it was a combination material thing. So we took the solder paste, we made some boards, we reflowed them, put them through testing, and were not able to produce failures. As soon as we then continued to rework the packages with a combination of paste and rework material that the supplier was using, we were able to demonstrate failures. As you can see here in the video clip on the right-hand side of the screen, and the 2 optical images you can see on the left-hand side. So when suppliers tell you about compatibility of materials, on some occasions it is very true. You can get a combination of materials which don't work successfully together. So it's something to bear in mind when you're looking at materials that you're going to be using. Same thing is true on these examples, but these were not related to rework and subsequent materials added to the mix. This is just compatibility of the materials used in the original set. We talked about QFNs. and there's another couple of presentations about QFN and reliability and improving reliability, which a lot of suppliers have been able to do by improving the wettability on side terminations and improving the long-term reliability with side terminations, incorporating dimples, secondary plating to give more mechanical strength, etc. So that's something that's positive within the industry. But with temperature cycling with QFNs, with traditional alloys, traditional SAC alloys, you might expect 1,000 to 2,000 temperature cycles, depending on the package size, the die size, and obviously the testing. What I'm showing you here is just some examples of some experiments that myself and Richard from the SMTA committee did, just to get a feel for what's actually happening and failures. And you can see these are conducted on low temperature joints. Initially at -55 plus 125, which is really outside of the window that you should be using. We repeated these tests at -40 to plus 110 with no visible signs of failure up to 1,000 cycles. But again, probably the most common reason for failure of low temperature materials is mechanical. It's not necessarily thermal expansion. But solderability has also caused me a couple of problems with low temperature materials. And this is just an example of a QFN which failed, where we were getting poor wetting on the pad terminations of parts. So again, I would urge you to look at testing parts if you ever concerned with wettability or solderability of these parts, and it is still seen sometimes as a problem. You can see in this particular example, this is just a video clip that I created, just showing separation, and this is even where that side termination was wettable, and there was a secondary plating operation conducted on the part. Some of you will be familiar. This is the Bob Willis cheapo test for solderability. Glass slide, print paste, place part, put it through reflow. If all the solder stays on the part, then you've got good solderability. So the samples on the left-hand side are great. The samples on the right-hand side of this slide are poor. It's as simple as that. However, obviously, if you want to do this testing, practical things, with convection reflow, it works fine. Vapor phase, just be aware potentially the packages can slide off the side of the glass. This is me being practical now. A couple of other things you can get, which I've never seen this to be a failure, I have to say, but burring on parts and also slivers on parts. So on the left-hand side, you can see some nice examples of tin slivers, and it's all to do with the way in which the parts are singulated from the package. So it's again something to look at. As I said, never seen it be a failure mode, but it's something to be aware of. You can, if you want, do traditional wettability, solderability tests with a wetting balance, as you see me doing here. It's hard work unless you use a camera. The camera, in my opinion, is vital for using what is considered to be the standard for doing solderability testing in our industry. And just an example of a squiggly line of one of my test samples. So the final slide I wanted to mention. So if you're looking at low temperature, which I'm very interested in, I'm not suggesting you go out and use low temperature today, but I'm very interested in understanding it through each of the manufacturing processes. But the only failure I've had personally to date has been wettability, solderability with some parts, and a mechanical damage to joints, which I'm sure some of you may already have experienced. So if you're interested in QFN LGA type failures, there is a free guide which you can get. I've listed here, it's a free guide to download. And I had to mention the Keith Bryant guide, which is available from your SMTA chapter office. Again, that's available free. Again, just focuses on BGA and BGA failures. So with that, I'd just like to say thank you very much for taking the time to listen. I hope I've been a sufficiently good warm-up for Martin and Chris. and hopefully there may be a few questions. Keith.
Thank you, Bob. Yeah, I'm just looking to see if I can put Bob's picture up.
Well, I talk, and then if I keep talking, the picture will stay.
Don't worry, we've got you up. So when you answer a question, I saw some hands. So if you, sir.
Okay, in the beginning of this presentation, there were LGA assembly, and some of the solder didn't put up to the component pads that were solder mask defined, I believe. And on the motherboard, the pads were non-solder mask defined. Is there any good reason or explanation for this open solder joints?
Did you hear that, Bob?
Yes, I did. It wasn't the intention in those particular examples to show solder mask defined and non-solder mask defined. The only area that that was true, if you like, was where we've got solder mask around vias and via holes. So that would be my comment. In terms of solder mask defined pads, there is an advantage, a subtle advantage of doing drop testing as you get smaller and smaller and smaller, particularly with hard alloys, because with hard alloys they are more likely to break, and as you go smaller and smaller and smaller, the weakest bit is the pad on the board. So it might seem strange, but having a resist defined pad is just something else to hold the copper to the pad. Okay, so you've just got to think of, how the failure mode does occur. So there's been a couple of studies on small BGA packages, ultrafine pitch, where people have used traditional design rules and solder mask defined design rules and found mechanically they were stronger and they were sufficiently stronger or reliable to eliminate the use of underfill, which is an expensive process.
Okay, any more questions? Oh, we got a quiet room, Bob. That means you're either very good or very bad, and I know the answer to that question.
Well, thank you very much, Keith. I really appreciate that.
So thank you very much, and also thank you for wearing the branded polo shirt.
Well, I'm never commercial. It's just in honor of the person who presented it to me when she retired from SMTA, and I was most pleased to receive it, and of course continue to wear it. You know me, I am not a commercial person.
Thanks very much, Bob, and thank you for taking the time to beam in for us. David, can you give Carly a shout, please?